Hey everybody, in the last video we solved an F equation, meaning that we arrived at the F statistic for a one-way ANOVA, or analysis of variance. Now in this video we need to do the follow-up to that. Once we've obtained a statistically significant F value for an ANOVA, we now need to do the post hoc analysis. That means that we need to figure out which groups were different from which other groups. So we'll walk through how to do that in this video. To catch you up if you haven't been following along, or if it's been a little while, there was somebody named Nadine in our scenario. Nadine came up with a new plant fertilizer and wanted to see which amount of fertilizer was most effective in helping these plants to grow as fast as they could. She had 4 different groups, including a control group, and her dependent variable was how long it took in days for these plants to reach the height of 6 inches. Here were her groups. She had a control group that received only water, a group that received only ½ of an ounce of the fertilizer throughout the soil mixture, a group that received 1 full ounce, and a group that received 2 full ounces in their soil mixtures. She had 7 plants in each of these groups, and there were equal numbers of these plants in each group then. That's semi-important. All right, and of course, as we saw in the last video, what we found was an F value. In other words, we solved our F equation, found an F statistic of 49.06. We found that that statistic occurs less than 1% of the time if there's no, at least theoretically, if there is no effect of the independent variable, the group, on the length of time that it took for the plants to reach 6 inches. So therefore, because it's such a rare statistic, this is statistically significant, and we can conclude that actually it made a difference. Now, where it made the difference, we don't know yet. That's what we need to do here. As you can see also, this is going to be important for later. We've had 3 degrees of freedom for our between groups variance. In other words, among group variance is really grammatically correct. And then 24 degrees of freedom for our within groups variance, okay? That's going to be important for later. So far, all we can say is that we know that there was a difference. There was an effect of the fertilizer on the growth rate. However, at this point, we can't say what it was. It might have made them all worse. It might have made only one of these groups much better than the control group, for example. It might have, maybe the control group wasn't different from any of them, but 2 of the fertilizer groups were different. We don't know yet. So that's where we leave off now. So this is where the post hoc analyses come in. A post hoc analysis tells you which of these groups is meaningfully different from which other group. There are lots of different kinds of post hoc analyses. We're just going to cover one of them. We're going to cover what is probably the most common one, and it's also relatively simple to calculate. Now, why they are different is because they each use different elements of the data to arrive at the conclusion that they reach. Some of them are more conservative, meaning they're a little less likely to say that they were different, and some of them are a little more liberal, meaning a little more likely to say that these groups were different. You read up on them, work on them in grad school or whatever you're doing. For now, we're just going to use Tukey's post hoc test. It's a relatively common one and relatively simple to calculate, as I said. The name of the person who invented it is Tukey, T-U-K-E-Y, not Turkey. Please don't mess that up. The test is called the Honestly Significant Difference Test, or HSD test. We will refer to it only as the HSD test for the rest of this time. All right, what it does is it figures out a criterion, some kind of amount of difference between 2 means that would be statistically significant as a difference. So if 2 means are at least that different, we can say those 2 means are actually meaningfully different, and this probably wasn't just an accidental finding. There really was an impact of the independent variable on their growth rate in this particular case. It's very similar to a critical value. The only difference here is that we're comparing the mean differences to the critical value. Okay, we'll walk through how to do this. Here's the equation. It looks just like this, relatively simple, not a whole lot going on here. Let's talk about each of these elements. We haven't covered them explicitly except for the little n here. So the MS within thing right there, that refers to the mean squares from the within groups variance. All that is the denominator. Once you've calculated almost everything in the F equation, the MS within is just what's left in the denominator before you finally do that last division of the numerator by the denominator. Okay, so I'll show you that. Yeah, exactly, it's right here. If you go back to our previous video, you can see that this was our F equation right before we did that final division to get our 49.06. So the ms within is just that denominator portion. So as you can see here, the value of the ms within is 1.19. So all we need to do here is plug 1.19 into the equation there. So as you can see, I've done that now. The next element that we can obtain is, of course, the little n. Now, little n in this case is the number of observations per group, the number of times we observed a value for our dependent variable in our groups. And in this case, we had 7 per group. So n would be 7, little n would be 7. If this were a capital N, that would mean the total, but it's not a capital N. It would be 28 in this case, right? But it's not. It's a little n, which means we're using the number per groups. Now, in this case, it's not a problem because we had equal numbers per group. In some instances, however, you will have different numbers per group. In that case, you need to use something, instead of the little n, you use something called a harmonic mean. Don't worry about that right now. You can look that up in my textbook if you are concerned about that. It's just in the post hoc analysis chapter of the textbook. You can also just Google it if that's a scenario that you're working with. All right. So the last value then, as you can see here, I plugged in 7 because that's what it is in this case, and our mean squares within is 1.19. Now this Q value is new. We've not seen that ever before. Okay, the Q value is something that is standardized based on whatever our ANOVA looks like, based on the characteristics of our ANOVA. In other words, it depends on the size of our groups and the number of groups at least, and the number of participants we have per group essentially, or I guess it's really total. In that instance. So what we need to do here is look up the Q value in an appendix of the textbook. So what we're doing here, again, we're not looking up the critical value of the HST, we're looking up just the Q value that goes inside of the HST equation. So it's almost like a play within a play. It could be a little much. So what we're going to do here is go to Appendix D of my textbook. If you don't use my textbook, just Google it. You can find out Q values or Tukey's HST Q values on the internet, and you can find all sorts of these tables. Here's a look at the Appendix D in my textbook. It looks very similar to this. Of course, I flipped down a couple of pages here. Now again, what we're doing here is we need the 2 criteria here. Number 1, we need the number of means that we're comparing in the null hypothesis. In this case, we had 4 groups, right? We had the control group, we had a ½ ounce group, a 1 ounce group, and a 2 ounce group. That's 4 groups. So we're going to be looking down this column of 4 means compared. And this says we need to know the degrees of freedom for our within groups variance. As we talked about, that was 24 in this case. And again, if you don't remember the equation, it's n minus 1 minus k minus 1. In this case, n was 28. 28 minus 1 is 27. K was 4 because we had 4 groups. 4 minus 1 is 3. And then, of course, 27 minus 3 is 24. So we have 24 degrees of freedom. Therefore, our critical value, we're going to start off with a p-level of 0.05. Down here is the criterion we'd be using for a p-level of 0.01. Again, we're going to start off with 0.05. Now, what's interesting here is we had a critical value of 0.01 for our overall F value. It's fine though. I really don't see any reason to have to use 0.01 as your statistical significance value for the post hoc test. Okay. Now, one little note here is it you might ask, is it possible? Can I find a statistically significant F value and then not find statistically significant post hoc analysis? And the answer is yes, sort of. It depends if you're using a more conservative post hoc analysis criteria or a test that has more conservative criteria, then it is actually possible that it would not quite be, it would be probably very close to statistically significant, but maybe not quite there. Anyway, that's maybe a little beyond what we need to do here. So our Q value is 3.91. We just plug our Q value into the equation like I do right now. As you can see here, 3.91 is our Q value, mean squares within value, and our little italicized n, the number of observations per group. And so all we do is now simplify the equation here. So that's pretty easy to do. 3.91 times the square root of 0.17. We reach 0.17 because we divided 1.19 by 7. And then we take the square root of 0.17 to get 0.4123. And I think I've rounded a little bit here. Multiply 0.4123 by 3.91 to get, of course, an HSD value of 1.61. Now, 1.61 is essentially our critical value here. Let's talk about that. So our HSD value is 1.61. What this tells us is our means have to be at least 1.61 days different from one another in order for us to say that those two means we're comparing are meaningfully or statistically significantly different from one another. Okay, now we're gonna do all of this. We're actually gonna practice this, and so you'll see how this works. But of course, before we could start comparing the means, we need to calculate those. And actually, it turns out we haven't calculated those up to this point in our entire ANOVA. So let's do that next. Now, I'm getting this data from a previous slideshow, from a previous video. So if you're not sure where I'm getting this, that's where I'm getting all this. I gave you this data earlier, and now we just take this. So this is the total value of the number of days it took for the control group to reach 6 inches. In other words, I took all of the plants that were in there, all 7 of them, took how many days it took each of them to reach 6 inches, and I added them up. That's all this is the total sum of each of those values. Okay? So of course, to get the mean, I just take 102 and divide it by 7, because that's how many plants there were. So I get an average of 14.57. In other words, for the control group, it took them an average of 14.57 days to reach 6 inches. Same thing for the half-ounce group. 65 divided by 7, it took that group 9.29 days on average to reach 6 inches. For the 1 ounce group, it was 11.43 days on average to reach 6 inches. And for the 2 ounce group, 15.57 days on average to reach 6 inches. So now I need to retain all of those means, because we're going to now do some calculations with those. Let's talk about how many calculations I'm going to need to make here. Okay, because we have 4 means that we'll be comparing to each other, and I need to compare every one to every other one, that means that I'm going to have to make 6 comparisons here. Let me walk you through why. First, I'm going to compare the control group to the half-ounce group. Then I'm going to compare the half-ounce group to the 1 ounce group. Then I'm going to compare the 1 ounce group to the 2 ounce group. So far I've got 3 comparisons. I then need to compare the control group to the 1 ounce group, which is 4 comparisons. I then need to compare the half-ounce group to the 2 ounce group. And then finally, I need to compare the control group to the 2 ounce group for a total of 6 comparisons. Now, of course, this rises a little bit every time depending on how many groups you have. If you have 3 groups, you have only 3 comparisons. 4 groups, you have 6 comparisons, and so on. So it increases. Now, if you're ever not sure how many comparisons you need to make, here's a nice little way to figure that out. It's the number of groups you have minus 1 multiplied by the number of groups you have and then divided by 2. In this case, we had 4 groups. 4 minus 1 is 3. 3 times 4 is 12. 12 divided by 2 is 6 for 6 comparisons. That will work every time if you're ever not sure. And of course, this is in my textbook as well. So now here is what we do for our post hoc test, right? I've put our means here just to refer to them so that you remember where we had them. Now what we do is compare each mean to each other mean. And our HSD value, or our criterion, our minimum mean difference that we need, is 1.61. So a lot of students confuse us and they say, well, 14.57, that's bigger than 1.61. That is not what we're doing here. We're comparing the mean difference to 1.61. So let me show you how this works. First of all, let's compare the control group and the half-ounce group. And again, we don't care about which one's positive or negative. And so really what we're talking about is just the absolute value of that difference. So 14.57 minus 9.29, those two means are different by 5.28. 5.28 is a bigger difference than 1.61. In other words, these two groups were different by 5.28 days, when the minimum I needed for meaningful difference was 1.61 days. So this is a statistically significant difference. I can now say the half-ounce group grew significantly faster than the control group. All right, let's do the same thing for the next comparison, the control group to the 1 ounce group. 14.57 minus 11.43 is a difference of 3.14 days. Again, 3.14 is bigger than 1.61, so that is a significant difference. In other words, I can now say the 1 ounce group also grew significantly faster than the control group. Now we'll do the third comparison, 14.57 and 15.57. That's a difference of only 1 day of difference. And so that is not enough, right? I needed a day, at least 1.61 days of difference, and this was only 1 day. So therefore, those groups weren't different. It looks like my fertilizer at this point, maybe even it doesn't weaken it doesn't make them grow slower, but it certainly just isn't the right mixture to help the plants grow faster compared to the control group. Now we can start comparing among these other groups here. So we'll do the ½ ounce group to the 1 ounce group. We did find a significant difference, as you can see. So actually it turns out that the ½ ounce group so far appears to be the most effective mixture. Now let's see if the 1 ounce group is still better than the 2 ounce group. As you can see here, it is, because it was the ½ ounce group is better than the 2 ounce group, I mean. So again, the ½ ounce group seems to be our best group. We've now done the comparisons with the ½ ounce group to all of them, and it was meaningfully lower than all of the other values. Now our last one, of course, is the 1 ounce group and the 2 ounce group, and actually the 1 ounce group was meaningfully shorter time than the 2 ounce group. Okay, so now let's put this all together. Okay, as we can see here, we already knew that Nadine's fertilizer had some effect on the plants. We knew that from the omnibus test, from the original test, without even doing the post hoc analyses. But what we didn't know is, did it make it worse overall? Did it make it better overall? Or what? Okay, now we know not only did it have a significant difference, but we also know that the ½ ounce group mixture was more effective than any other mixture that we had, including the control group. And so we can very strongly recommend that ½ ounce ratio, or whatever it was, in her plant soil. And that should be what she recommends, at least so far. Now what she might want to do is do some follow-up studies to find a little more nuanced differences around the ½ ounce. Maybe not go up to a full ounce, for example, and see if actually she could get away with a ¼ ounce, maybe, right? So then we also know that 1 ounce was even better than the 2 ounces, of course, and also better than the control group. However, we know that the 2 ounce group actually was no different from the control group, and so we would definitely not recommend the 2 ounce group going forward. So far, a ½ ounce group appears to be the most effective. Okay, and that's that. One little caveat here I'll say also is it actually turns out that you can actually just ignore the omnibus test and still just run post hoc analyses on your data, and you'll actually arrive at the same result. However, we need many of the elements within our ANOVA in order to do other things like effect size and things like that. And so we generally do report it anyway. In fact, I don't think I've ever seen an actual study that reported only the post hoc analyses of an ANOVA without the ANOVA. But the 0.05 criterion is built into the post hoc analyses, so it's kind of an interesting thing. Anyway, that's more than maybe we need to know. Okay, next time we will calculate an effect size, or at least we'll try 2 measures of effect size for the ANOVA, and I'll show you how that works. I'll see you then.